To start off 8.5, you are given a line and a plane in 3 space, and there are 3 possibilities for the intersection of the line with the plane. The first possibility is this one here. So the line and the plane intersect at a point. This is a point, and there is a line and the plane. There's exactly one solution if this occurs. Another possibility is when the line lies on the plane. So every point on the line will intersect the plane. If this occurs, then that means there are an infinite number of solutions. The last possibility is when the line and the plane do not intersect. So this means that the line is parallel to the plane, and therefore there would be no solutions. So now we will be looking at some knowledge-based examples. The first question consists of determining if the line and plane will intersect or not. To start off, given the scalar equation of the plane, you have to sub in the parametric equations into the scalar equation of the plane. So when you sub in the parametric equations into the scalar equation of the plane, you get t equals to -1. Therefore, you have to find what point they intersect at. So then you sub in t equals to -1 into the parametric equations to find the single point. So after subbing in the value of t into the parametric equations, you get a single point where the plane and the line intersect, which is 3, 0, and -1 for x, y, and z. Now let's do a second knowledge-based example. So here's a scalar equation given, and here's a parametric equation. You will do the same as you did in the first example by subbing in the parametric equation into the scalar equation. So for this equation, you aren't given the parametric equations, but you are given the coordinates. So start off with the x value. You have to use the x values in the 2 coordinates. So that would be -2 plus 3t, because you have to remember to expand t into the brackets. For y, it would be 4 plus t. For z, it would be 1 minus t. And that would equal to -1. And then you would expand and simplify this equation. After expanding and solving for t, you get t equals to 0. Therefore, the equation is true for all values of t. Any point on the line is a solution, and the line lies completely on the plane.
We're going to start off with example number 3. So this problem is to find an equation of a plane passing through the point -1, 3, and -8, and parallel to the plane 3x minus 4y minus 6z equals 9. So in order to solve this, we have to remember what the equation of a plane in normal form is. So any plane that contains the point x1, y1, and z1, and has a normal vector of n equals a, b, and c, has the equation a x minus x1 plus b y minus y1 plus c z minus z1. So in our case, we're given a point of -1, 3, and -8, which would represent our coordinates of x1, y1, and z1. And we're also given the equation of a plane, 3x minus 4y minus 6z equals 9. From this, we can find a normal vector of 3, -4, and -6, representing our a, b, and c values. So now, in order to solve, we have to think of this in a diagram form and envision what the problem is actually trying to say. So based on this diagram, we are given a point on our green plane here, and we're also given our purple plane, which is this plane over here. And as you can see, we have a normal vector that is orthogonal to our purple plane, and that normal vector would be this. And this normal vector also is orthogonal to the plane that we are trying to find the equation of, that contains this given point. So now that we can envision what this problem is looking for, we can just simply substitute what we know into the formula for the equation of a plane and solve. So our a value would be 3x plus 1, because minus 1 equals plus 1, plus our b value, which in this case would actually be negative 4, y minus 3, and then negative 6, z plus 8. So now we can simply distribute this and solve. So solving for, or adding or subtracting the terms that don't have any variables attached to them, we would end up with this. And to finish off this equation, we simply move the negative 33 to the other side, which gives us this as our final answer. 3x minus 4y minus 6z equals 33. And that is the equation of the plane that contains this point and is also parallel to this given plane. Okay, so now we're going to be starting off with example 4. And this question says, determine the angle between the line vector r equals 1, 2, and negative 1, plus t, 1, negative 1, 1, and the plane 2x minus y plus z equals 4. So this problem is very unique because as you can see, this line intersects with the plane that is given, but since it lies on the plane, it would have multiple intersection points. So we have to find the angle between this line and the plane. So we have to find this angle theta. And currently we are given the normal, which is 2, negative 1, and plus z based on this. This would be our normal vector over here. So if we wanted to find theta, we would have to subtract the value of this portion, the angle between the normal and the line. We would have to subtract that from 90 degrees because together this would be forming a 90-degree angle. So we would have to do 90 degrees minus, I'm calling this theta 1. And I've labeled this intersecting line L1. So in order to solve this, we are given the direction vector, which is 1, negative 1, and 1 based on this parametric, this equation here, the equation of the line. And we're also given the value of our normal vector over here. So in order to find the angle between the normal and the intersecting line, we can use the dot product of the direction vector and our normal vector. So to find the dot product, we would have to find the cos of theta 1 over here. And we can do that by multiplying the dot product of m times n and dividing it by the magnitude of m and n individually. And when we solve this, we end up with this answer. So to find our final answer, we just have to take cos inverse. So that means the angle between the normal and this line, the line that intersects with the plane, will be 19.47 degrees. So now that we have this angle, in order to find the angle theta, so the angle between the line and the actual plane, all we have to do is simply subtract theta 1, which is 19.47 degrees. So that means theta equals 70.52 degrees or 70 degrees.